Hello and welcome. My name is Sean Lacey of Lacey Maths and Stats Consultancy. In this video is a demonstration on doing power analysis in GPower and RStudio. The focus for the power analysis will be in relation to doing a paired t-test. I'm going to look at doing the analyses twice using each package, but then doing three separate types of analyses. So the first will be looking at a sample size calculation, then looking at profile plots, and then finishing up with multiple profile plots. I'm going to use GPower first, mainly down to, I suppose, that was the first package I would have used when it came to doing power analysis. And I suppose, as you might have seen in my recent, the videos that I have up on YouTube at the moment, that there's a lot of videos on RStudio and with a focus on data transparency and stuff. So I feel that it's nice to, I suppose, develop code or develop script in RStudio that actually replicates the results of GPower. And I suppose that's what I'm going to show in this video, how we actually can get the same results using the two different packages, which is always just a nice thing, I suppose, for kind of validation purposes and so on. Okay, so the data I'm going to use will be data that we would have looked at in a previous video. So I would have uploaded a video, just go to the playlist there. So I would have uploaded, I suppose, 3 videos on sample presentation of statistical test results. So there would have been one sample t-test with the Wilcoxon test, independent sample t-test with Mann-Whitney-U, and a paired sample t-test with the Wilcoxon test. I'm going to continue on with the data that I would have shown you, I suppose, that we would have looked at for the paired samples t-test. So I'm going to look at that script. So the script for this would be actually, there's a link on this video for Google Drive, and in that, so you'll see actually all the script that would have been used to generate the statistical test results. Okay, so I'm going to just do a power analysis as a follow-on from that section. Okay, so just as a quick refresher, so important data, looking at the data is looking at subjects' triglyceride levels over the course of 4 months, and for the illustration for presenting the statistical test results on the video that I just pointed to there on YouTube, we focused on males comparing their baseline against 1 month triglyceride levels to determine whether or not there's a difference. We are looking at the assumptions, so we looked at box plots to compare the two groups. Then we looked at the descriptive statistics that we be interested in, and then moved on to doing a paired t-test. Worked out the effect size. Then the next section here was the effect size, and then finally would have been just putting all the results together to and I suppose the point to that then was just kind of a way of presenting statistical test results. That was kind of the focus of that video. So I'm just going to quickly just highlight all that script there, going to run that off. That all seems to be going fine. A few packages are installed, so we can just, our libraries loaded, so you can just see, look, the triglyceride levels decreased from baseline to 1 month. They were decreasing, but when we look at the statistical test results, and I'm just kind of going to the end point here, we actually have it here, sorry, you can see that the difference, so the decrease of 21.2 milligrams per deciliter was found to be statistically insignificant. Okay, but then when you look at the standardized mean difference, the effect size, the difference that we can see here in the box plots is actually classified as a moderate difference. So what we'll be looking at then is, well, and this here will be an ideal candidate for, well, if we increase the sample size, more likely the difference that we've observed here, 21.2 milligrams per deciliter, would be statistically significant. So then if you're going to increase the sample size, what would you increase the sample size to? Okay, so that's what we want to try to look at. I'm going to first determine what the sample size should be. This is kind of the part 1 here that I mentioned here in this part slide here. So first look, what actually would the sample size be? What I find when I present this sample size, all you're kind of getting back is a number, which is obviously quite good. It's a good number, but it's nice to kind of see, look, what's happening to the left and right of that. So what's happening to the left and right of that is ultimately a profile plot. And then what I find is useful is sometimes is producing multiple profile plots, just so we can see, look, that when we increase our sample size, if there's a slight variation in the effect size, which ultimately means there's a slight variation in what the sample mean and sample standard deviation turn out to be, how does this affect the power and so on like that? Okay, so that's kind of the approach to this. So I'm going to go to GPower. Well, first what I want to do is here, I want to come back here because I need that effect size, and I'm going to come here to GPower. Okay, so what I'm going to look at here, I suppose let's set this up first. So we're looking at the t-test family. multiple statistical tests that we can do under a t-test. The one that we're looking at is where we've done a pair t-test, so this is called matched pairs here. There's a good few different types of power analyses. It ultimately depends on what you're looking for. Here, for this video, we're looking for a sample size, so that's the power analysis that we're doing for this video. You could do a power analysis where you might be trying to work out, look, what would the power be based on knowing the effect size, level of significance, sample size. You might want to work out what the level of significance would be given that you know the other three things. Okay, so there's various types of power analysis. It depends on what you're trying to work out, but ultimately what we're trying to work out is a sample size where we know what the level of significance, the power, and the effect size are. Okay, so we're going to pick that one. It's a two-tailed test that I'm saying that we would have done, so we're going to focus on the two-tailed. We want to put in the effect size, so the effect size we can put in is 0.68 here. I much prefer when we are putting in numbers that we, I suppose, have them as accurate as possible. In the script that we have here, you can see that I rounded the effect size to 2 decimal places. But I think it's nice to actually maybe have it as a bit more precise if possible. So I'm just going to come back here, and this is it here. Look, here's the effect. 3.1 is what I called it. And we can see here that it turns out to be like that. Actually, even if I get it a bit more precise here, maybe this one, if I run that off there, we can see here, we just get it a small bit more accurate. So I'm just going to take all that information there. So here, so why won't you copy there from, sorry, I just copied it the wrong way, sorry about that. And I'm going to just copy that into here. There we go. Okay, it's just to be a small bit more precise, that's all. Then the level of significance, I'm going to work off 0.05 level of significance. There's usually a ratio of 1:4 between the level of significance and the statistical power. So the statistical power is the probability of correctly rejecting the null hypothesis. So that would then mean I'm going to work off a 0.8 power in this case. And if we work that out, we're going to end up with a sample size. We require a sample size of 19. Now, I know that I'm kind of quickly going through the stats here, but what we actually would have had in the stats here is we would have actually had a sample size of 9. So this will be seen as a kind of nearly like a pilot study, if you want to think of it like that. So there was a sample size of 9. The difference that was observed was a moderate difference, but unfortunately it was statistically insignificant. So what G power here is telling us by us doing a power calculation is that if we increase the sample size to 19, so increase it by another 10, that then the difference that we'll observe will be statistically significant with a power of 80%. Okay, so that's kind of the first part of where we just work out a statistical power. The next part then to this, what I wanted to do is just look at the profile plots, which is where you're looking at this XY plot for a range of values. So I'm going to click that. I'm going to keep this as simple as possible. I'm just going to go with the default what G power is going with here. So it's just plotting the sample size against the power. I feel this is a nice visual to get back, because you're kind of just seeing, look, what actually happens to power as your sample size increases or decreases, and vice versa. Okay, so I'm going to leave it as the default where we're looking at the power going from 0.6 up to 0.95 in increments of 0.01. I'm going to draw that plot, and there we have it. Okay, so I feel that that's a nice plot. It just kind of shows, look here, this is where I suppose the result that we would have got back from G power kind of in the part 1 analysis. Now we're getting the profile plot. So what we can see here is as we increase the power marginally up to the right, what impacted that, or sorry, if we require the power to, I suppose, to be a small bit higher, what impact does that have on the sample size? Or if our sample size decreases, if we don't actually hit the target 19, what does that potentially have, impact does that have on our power? So I think that's a nice kind of result. So that's the second part. The third part, which is where you're looking at multiple profile plots, would be, I suppose, when you're increasing your sample size, ideally you're basing it on the fact that your increased sample size would have this is ultimately the same effect size, which means the means and standard deviations you get back will be the same, we would say, as your pilot. Sometimes that mightn't happen. Sometimes when you increase your sample size, your means and standard deviations will fluctuate from what your pilot was. So that ultimately means your effect size will potentially be different. So how does that impact then the power and your required sample size? Should you be kind of allowing a small bit of leeway with it? Okay, so this is where the multiple plots, I would feel, comes into play. So just down here, like, there's loads of different options here but here for the plots, I'm just going to look at where I have 3 plots. I think too many plots makes it too confusing. So what G power is doing here is it's plotting, I suppose, the power against the sample size, same interval for the power here. And then here, what it's saying here is it's looking at the effect size where it's just defaulted. Now I'm going to change this, where it's defaulted to saying that the effect size is going from 0.1 in steps of 0.05, and then there's going to be 3 of those. Okay, so what I'm going to do here is I'm going to change this. So 0.68 roughly was the effect size that we have. So I'm going to put that as the middle one. So what I'm going to say here is, if I said the effect size goes from 0.65, and I'm going to put it up in increments of 0.03. So that will mean 0.65, 0.68, 0.71. They'll be our 3 effect size for this. And I'm going to leave the level of significance as 0.05. If we draw that, we end up with this result here. Okay. So what we can see in this case here is, if our effect size decreases so that the difference that we've observed isn't as strong, we'll say no, it's still technically be in the moderate category if we're going by the Cohen's-d classification here. So if the effect size, if the difference that we've observed isn't as strong, which means we have a smaller effect size, well then realistically we need a larger population, or larger sample size to actually match the 80% power if that's what we're working from. Okay, so we can see here with the smaller sample size, the smaller effect size, we need a larger sample size to give us an 80% power. With the larger effect size, which is the green here, the larger effect size, we need a smaller sample size to give us the same power. So if we want to look at it like that, okay? And I think that's going to be a nice graph as well, because it kind of just shows the blue here is kind of based on your pilot study. And what if when you increase your study, you increase your sample size for your main study, what if things are better, which would actually be the green, or what if they're slightly worse, which would be the red. So it just kind of gives this kind of, it's nearly like a margin of error to your results, okay, which can be quite nice. Can be quite nice. Okay, so that would be the 3 things that I wanted to show you when it comes to the G power, which are quite nice. And again, we're only focusing on the pair t-test here for this, but we can just see what the interest is like in the video, and I might look at other versions of doing the power analysis, maybe for, we could say, other types of t-tests, or even looking at it doing for the ANOVA, or looking at it doing for proportions and so on, okay? But ultimately, I suppose what I'd like to then be able to do is to replicate these 3 sets of results. So the first one was this number of 19, to replicate that, to get it out of RStudio. Then the second thing would be to actually, just where we had the single plot, so the single red plot, and then how we get these multiple plots. So I want to just do that using RStudio. So I put together some script for this. So this won't take too long to kind of work through. So here, this is where the sample results. So all this text, all the script up here, this was I suppose what we would have seen in the previous video. Okay, that's up there in the playlist on my YouTube channel. Okay, so what I'm now looking at doing here is I'm looking at trying to, where are we gone? Trying here, yeah. So I'm looking at trying to work out what the power would be. So we have an effect size of 0.68 to 2 decimal places. I want to use it more accurate here, to more decimal places. If we work off an effect size of 0.68 with a level of significance of 0.05, we're working with an 80% power, and we're obviously doing a pair test, two-tailed. What would our sample size actually be? So I'm going to use the PWR package. So I'm going to load the library, and I'm going to run off this power.t.test function and call my result res, just for the sake of it. And when I do that here, I'll end up with this result. Okay, so what this is telling me here is I've told OR that I'm working off the effect size that I gathered up in the previous script. I've told OR my level of significance, told OR the power, so it knows by default, since I've stated those 3, it knows what I want to work out, which is the sample size. And I'm just telling OR what type of t-test I have. That's quite important. Okay, that actually has an impact. Okay, so are you doing a one-tailed, are you doing an independent, or is it paired? That's very important. Then here, is it a two-tailed test that you have, or is it a one-tailed? And if it's a one-tailed, is it less or greater? They're all quite important. Okay, so you just want to make sure that you kind of state them. All right. When we do this, then you can see here that it gives us the sample size. So it's telling us that the sample size is 18.92. So as you can imagine, we're dealing with participants. So you would always round that up. See? So what we would look at is the ceiling of the result $n for that attribute, and then we'll just round that up to 19 there in that case. Okay, so that 19 is the result that we got back from G power here as well. Okay, so that's quite nice. I think that's the first step. Okay, the second step then that I want to look at here is, just going to quickly go back to this one here, is where we had the single red plot. Okay, so if we had the single red plot here, this is what we had. I wanted to see how do we replicate this in G power. Okay, so ultimately what this is doing is it's doing, if we actually counted all these open kind of circles here, it's actually done 36 power analyses. So that's what we want to do. We want to run off this function 36 times. So if you want to run off the same function over and over again, ultimately what you're looking at doing there is creating a loop. Okay, so I'm going to try to, I just want to replicate it as best as possible to what G-Power actually has here. So I'm looking at creating a vector for power. So I'm going to, because I want 36 power results. Okay, so I'm going to create a vector. My first value starting point will be 0.6. It goes up to 0.9 in increments of 0.01. So then I just work out how many values that gives me. What that will give me is 35, because it's not counting the first one. That's how this calculation would work. So I just need to make sure I add on +1. Then I'm obviously for each power there's going to be a corresponding sample size, so that ultimately means that this should produce 36 sample sizes, which when you think of it here, that's what they actually have. Like if you count all these dots and go all the way across, you're going to get 36 different sample sizes, so that we need to create a vector for that. Then I'm just going to do a for loop. The for loop here is basically looking at the power as it's incrementing up from each going up 1 steps of 0.01. Then it's using that power.t.test function for the various power types, and we're going to just looking at mainly interested in isolating what the sample size actually would be. Okay, so a few bits then to that, but you can see it here, and sure you can run it off then yourselves. And then all I just did at the last bit here is I just created a data frame of the power and the corresponding size that we're actually getting back. Okay, so I'm just going to run that. I get those results. Now what I'm actually just going to do here, this is kind of a nice thing here, so I'm going to just view, what's that called? I called it result 1. I'm just going to view that here. Okay, so there are various, so when the power, various I suppose power sample sizes would be. Okay, now what if we just come back here to G-Power, just let me see here, up here with the graph there's a tab for table. And for this tab for table, now it might necessarily be the exact now to like G-Power is to 4,000 places, or RStudio is to 5. But if we just look at the power of 0.6 over here, 12.5783, 12.5783, very nice. I won't go through them all now, but if I just look at the 0.671 here, 14.42901, 14.4290, perfect. And I'll do one more. What's the last one I can see here? Look, 13.72. and 15.94810, 0.72, 15.9481. So they're actually matching. Now you might, if you go through them all, you'll see maybe they might be off by the 5th decimal place, but overall you can see, look, these are giving us the same results, which is obviously ultimately what we want. But what's just nice with doing it in G-Power is we obviously have the script now to kind of back that steps up. The next thing now is just to do the plot. So it's basically just kind of a scatter plot is what we're kind of, or more, I suppose in a way it starts off as a scatter plot. That's what I'm saying here, plotting the points, but then obviously I want to join up the points, and I color the core of them red to make it as close as possible to what we have in G-Power. This is just the default, and I mean, I suppose you would have seen this in my previous videos that when I produce these graphs, I like to just first nearly get the default one, and then I look at how I'm going to better it. So I look at a particular form, I suppose, just for formatting, labeling the axes would be quite important, scaling the axes is important. And I think that would be mainly what I would have done with this. When I was, I suppose, labeling the axes, I like putting in 1 minus beta, because even with G-Power, that's what it actually has. It is put in 1 minus beta here, so that would just mean using the expression function here. So where is that? Just scroll down a fraction. Where do I actually have here? Here's the expression function. Okay, so we can just use that, which is a nice one. So I'm just going to open that up in this fresh window like this, and here's a result. Okay, so you can see, like everything in RStudio, it takes time to kind of put together the script, but once you have it done, that's it, job done then, alright? So what we actually have here is we're getting the same results that we have got in G-Power, but what is the bonus of doing it this way in RStudio is that we obviously have the script for that, which is basically our data transparency step, which is quite good. I obviously, you know, from my previous videos, I'm a big advocate of that where possible. Okay, so that's that bit. The next one I just want to do is I'm just going to look at the tree again. I know now it defaulted here 0.65, but this will be quite fast. 0.03. Draw that. So I just want to look at that. Okay, so I'm going to do this one next. I won't spend time matching the colors. When we do it in RStudio, the colors are actually just going to be swapped around. The red and the green are going to be swapped around. I'm just not going to do that because I want to try to keep the video, I suppose, somewhat short, and I suppose keep the text as, I suppose, the script as nice as possible. Okay, but here for this, what you can see here is basically what I did here is for the first plot is I set up the power as a vector and my sample size as a vector, and then created a for loop based on how many calculations I wanted to do. It's the same process again. So here there was 36 power calculations. I want to repeat the same process, but this time 3 times. So 36 by 3 will give 108 power calculations, and it's the reason there's 3 times is because of the 3 effect sizes. So what I did here, and look, there's loads of ways of doing these things, but I looked at creating a nested for loop. Okay, so I looked at the idea of the power vector with a start and end points. Then I looked at the effect size as a vector with a start and end points. Okay, so I picked the 3, I suppose, points that I wanted to. I decided I would set it up as a matrix then, so the sample size in the previous plot I set it up as a vector. Here I decided I'd set it up as a matrix where each column will represent the power, the size in relation to a particular effect size. I felt that that would just be a nice way of doing it. You can see R is giving me a bit of a red dot here. It doesn't like that I'm setting up a blank matrix, but ultimately that's what we want it to be because we're going to populate it here in the for loop. Just to make sure that it's actually set it up correctly, I just did the dimension of the size here, which should turn out to be 36 trees, so yeah, 36 rows, 3 columns, and then it's just going to be a nested for loop. So it's very similar to the previous script, except I just have this outer for loop which is looking at the 3 effect size increments. Okay, so it's going to look at the first effect size, then go into the inner for loop and going to do the 36 power calculations for that effect size, come back out, increment the effect size, go back in, and then do another 36 and continue on like that. And then I'm just going to pull the results together then by creating the data frame of the power with the size. So what this answer here will end up being 4 columns, and again I'm going to compare that result. I'm calling it result 2. I'm going to compare that result to what G power gives us. Okay, so that's everything I need here. That seems fine. Okay, so this just to see. So you have all the script there for that. What did I call this? I call this result 2. So I'm just going to view that. We have it here. Come back into G power. Just going to go to the table. I just think this is a nice thing just to check. Now I won't check. I'll just check 2 rows. So I start off with the first one. Look, 0.6 power, 13.61, 12.61, 11.74768. And if you look at them, I won't read them all out, but if you look at them, they're actually marrying up perfectly. Okay, the one thing G power is the 4 decimal places, RStudio is the 5 by default. I could have obviously rounded the RStudio ones to 4 if I wanted to. If I just go down to the 13th row here, 0.72, we'll see, look, 17.31, if 17.3124, look, 15.9999, 15.9999, and then 14.84 and so on like that. You can see that's marrying up perfectly, which is really nice. Really, like, you know, just kind of, you know, it's so nice to have that kind of safety net, because G power is quite a nice package, and now we're basically developing a script in RStudio that will actually give us the same results. Okay, so I have done that. Then the last, all I just wanted to do differently here for this, so if we viewed that, where's that result 2, is to just call the columns x1, x2, x3. So I just wanted to give them the names, felt that'd be easier, so I called them 0.65, 0.68, 0.71. Now it's not necessarily that I'm a big fan of calling variables by numbers, but I suppose I just knew where I wanted to go with this, because I basically wanted to change the data frame from a wide format to a long format. The reason for doing that is ultimately to do the plot then. Okay, so that was the reason of doing it. And then when I was doing the plot, it was basically looking at kind of a grouped, kind of like a scatter plot essentially, where it's going to be grouped based on the various effect sizes. So you can see that it's very similar structure to the previous scripts up above, except all that we actually have here is we're going to have a fill now based on the effect size. Okay, so I just changed the names, so using the names function. Then I used the gathered function from the dplyr package to, sorry, not dplyr, tidyr, to put it in a long format, and then I did the plot. So I'll do it in that stage first. Then I'll just generate the first plot here, and actually look, it went to the window that I had already opened here, so we'll go to that one. So that's quite good. Only all that's different here, now I'll better it now a small bit. All that's different here actually, sorry, I thought it was the outer ones were swapped, but it was actually the blue and the green are just swapped here. Obviously we could just change, if we really wanted to match the colors with G power, we could change them, and obviously in RStudio we've kind of a closed circle, while in G power they have an open circle. Look, I didn't want to go into that finessing of it, but obviously that could be something that you might want to do yourself, and look, that's absolutely fine. But you can also see, look, that we're actually getting the same results. I'm just going to kind of better, or it's just a fraction, just by labeling the axes, scaling it and so on like that, increasing the size. So let's do it this way, and this is the finished product. Okay, so I think that's quite nice. What is obviously really nice, I know it takes a bit of time, but what's nice is basically we've done the same analyses. We did it twice using 2 different packages and got the exact same answers. And obviously the G power is brilliant, and like what I said before is G-Power would have been, I suppose, my first package I would have used when I was doing power analysis a good few years ago. But obviously in more recent times I'm using RStudio, so I much prefer, like, when I'm using a package that I can nearly try to do all the work in that one package, and obviously this is just kind of a way of showing how to actually do that here. Okay, so hope you found that good. I might do a few more power analyses videos, maybe on the ANOVAs and proportions. I said that earlier. I can just see maybe what the feedback is like on this. Again, like all these, when you start, I suppose, looking at script in RStudio and stuff, there's more than one way of doing it. People might have more succinct types of code that they might like to comment on if they want. So I mean, comments are more than welcome. I've said this at the end of previous videos. I'm more than happy to get feedback on these. I'm very happy for that. I mean, this is basically, the YouTube channel is kind of essentially a platform for that kind of communication if you're interested in it. So feedback is much appreciated, and then if you find that the video overall is good and you like the kind of the message in it, then liking it, sharing it is always much appreciated, and subscribing to the channel, and you'll get updates on when the later, I suppose, power analysis videos will be uploaded. Okay, but for the moment, look, that's actually it. Thanks very much for your time, and till next time, all the best.